What if I told you that time travel might already be possible? Not in the way Hollywood portrays it, with sleek time machines and glowing wormholes, but in ways that scientists are only beginning to understand. Imagine stepping into another era, witnessing the rise and fall of civilizations, or even catching a glimpse of a distant future. Could it be that time travel is more than just fiction? Could we already be on the edge of unlocking its secrets? Humans have been captivated by the concept of time travel for centuries. Ancient civilizations told stories of gods and spirits who could move freely through time. Hindu mythology speaks of King Raivatakakudmi, who traveled to the heavens only to return and find that many generations had passed on Earth. In Japanese folklore, there's the tale of Urashima Taro, a fisherman who saved a turtle and was taken to a mystical underwater kingdom. When he returned home, hundreds of years had gone by. Even early philosophical debates from the Greeks and Romans touched on the possibility that time might not be as rigid as we perceive. But it was the birth of modern science that transformed time travel from legend into something that could be mathematically and theoretically explored. In the 20th century, Albert Einstein's theory of relativity shattered our understanding of time as an absolute force. Instead, he showed that time could stretch, bend, and even slow down depending on speed and gravity. Suddenly, the idea of moving through time wasn't just fantasy, it was a scientific possibility. This sparked a revolution in physics and pop culture alike. Books and movies flooded the imagination of the public, from H.G. Wells' The Time Machine to blockbuster films like Interstellar and Back to the Future. These stories weren't just entertainment, they were reflections of our deep curiosity about what might be possible. Could there be a way to break free from the constraints of time? Could we rewrite history or glimpse into the unknown future? Despite the fascination, the scientific community remains divided. Some argue that time travel violates fundamental laws of physics, while others insist that it's simply a matter of understanding the mechanics. Even Stephen Hawking, one of the greatest minds in physics, was skeptical but left the door open to possibilities, famously hosting a party for time travelers, only announcing it after the fact to see if anyone would show up. No one did, but that doesn't mean time travel is impossible. It just means we haven't figured it out yet. As technology advances, we're beginning to see real-world experiments that hint at time's flexibility. Astronauts aboard the International Space Station experience time dilation, aging slightly slower than people on Earth due to their speed and altitude. Atomic clocks, the most precise timekeepers ever built, have confirmed that time runs differently at varying altitudes and velocities. Some physicists believe that with the right conditions, whether through wormholes, quantum mechanics, or exotic particles, time travel could one day become a reality. In this video, we'll explore 5 of the most mind-blowing theories about time travel that are backed by science. From the paradoxes that challenge our understanding of causality to the mind-bending physics that could make traveling through time possible, each theory will take us one step closer to answering the ultimate question: can we really travel through time? Let's dive into the first theory, one that has puzzled scientists and philosophers for decades: the grandfather paradox. The grandfather paradox, a classic time travel dilemma. Time travel has always been surrounded by paradoxes, logical inconsistencies that challenge our fundamental understanding of cause and effect. Among these, one of the most famous and perplexing is the grandfather paradox. This thought experiment has been at the heart of debates about time travel for decades, raising deep philosophical and scientific questions. If time travel were possible, would we be able to change the past, or is history unchangeable? More importantly, if we could alter past events, what would happen to our own existence? Explaining the grandfather paradox. Imagine this. You build a time machine and travel back to the past, long before you were born. Out of curiosity, or perhaps by accident, you prevent your grandfather from meeting your grandmother. Maybe you interfere in their first encounter, or something you do causes one of them to make a different life choice. Because of this, your parents are never born. And if your parents never exist, then you, too, never come into existence. But if you never exist, then how could you have traveled back in time to change history in the first place? This paradox creates an infinite loop of contradiction. The moment you prevent your grandfather from meeting your grandmother, your own existence is erased from history. But if you never existed, you could never have traveled back in time to alter the past, meaning your grandfather's life would proceed as it originally did, allowing your birth to happen after all. This logical loop, known as a causal paradox, is one of the strongest arguments against time travel to the past. This dilemma has fascinated both scientists and philosophers for years. Could the universe allow such an event to happen? Or would there be a natural safeguard preventing paradoxes from occurring? Some scientists believe the universe has a way of self-correcting, ensuring that time travel wouldn't disrupt the natural flow of history. Others propose radical solutions that could bypass the paradox altogether. Scientific perspectives. Does the universe self-correct? One of the leading theories attempting to resolve the grandfather paradox is known as the Novikov self-consistency principle. Proposed by Russian physicist Igor Novikov, this idea suggests that time travel is possible, but only in ways that do not create contradictions. In other words, even if you were to travel back in time, you would never be able to change any event that would create a paradox. The universe, in a way, would course correct itself, preventing you from altering history in a way that erases your existence. For instance, if you attempted to stop your grandfather from meeting your grandmother, something would always intervene, perhaps a sudden accident, an external event, or even your own subconscious preventing you from following through. This concept has been explored in popular science fiction, such as the movie 12 Monkeys, where a time traveler is sent back in time to stop a catastrophe but ultimately ends up playing a role in causing it instead. According to Novikov's principle, events in time are fixed and cannot be changed, even by a time traveler. But what if time travel operates differently than we assume? Could there be an alternative explanation, one that allows multiple realities to coexist simultaneously? Quantum physics and the multiverse theory as possible solutions. If classical physics struggles to resolve the grandfather paradox, perhaps quantum mechanics can provide some answers. One of the most intriguing theories comes from the many worlds interpretation, a concept in quantum mechanics that suggests every possible outcome of an event actually happens, but in separate, parallel universes. According to this theory, if you were to travel back in time and prevent your grandfather from meeting your grandmother, you wouldn't erase your own existence. Instead, your actions would simply create a new timeline, a separate branch of reality where you were never born. Meanwhile, the original timeline where your grandfather met your grandmother would continue to exist separately. This concept aligns with Hugh Everett's many worlds interpretation, which argues that each quantum decision leads to a branching of the universe into multiple versions. In this scenario, every time travel event creates a new divergent reality rather than altering the original past. Could this mean that time travelers, if they exist, aren't actually changing history but merely jumping between parallel worlds? This idea has been widely explored in fiction, such as Marvel's Loki series and DC's The Flash, both of which depict alternate realities created through time manipulation. But is there any actual evidence that supports this theory? Real-world case study: Polchinski's paradox and mathematical challenges to time travel. A fascinating twist on the grandfather paradox comes from physicist Joseph Polchinski, who proposed a variation of the paradox using a closed time-like curve, CTC, a theoretical loop in spacetime that allows for time travel. Polchinski's version involves a billiard ball traveling through a wormhole and emerging in the past. In this setup, the billiard ball is sent into the past at a precise angle that ensures it will collide with its past self, preventing it from ever entering the wormhole in the first place. But if it never enters the wormhole, how does it travel to the past to interfere with itself? When physicists attempted to model this using mathematical equations, they found something surprising. Solutions existed where the billiard ball avoids creating a paradox by striking itself at just the right angle to allow both versions to coexist. This means that, under the right conditions, the laws of physics might prevent paradoxes naturally, supporting the Novikov self-consistency principle. But what if paradoxes aren't prevented? What if time travelers simply have no control over how events unfold? Controversial insight. Could time travelers already be among us? One of the most controversial ideas surrounding time travel is the possibility that time travelers are already here, but unable to alter history in any noticeable way. If Novikov's self-consistency principle is correct, then even if someone from the future were to arrive in our time, they might be bound by the universe's rules, preventing them from revealing themselves or making significant changes. There have been strange anomalies in history, unexplained artifacts, futuristic-looking figures in ancient photos, and sudden advancements in technology that some speculate could be signs of time travelers. A famous example is the time-traveling hipster, a viral photograph from the 1940s showing a man wearing modern-looking sunglasses and a printed t-shirt, completely out of place for the time period. In another case, the John Titor phenomenon captured the internet's attention in the early 2000s. A man claiming to be a time traveler from the year 2036 appeared on online forums, sharing details about future events, advanced technology, and government conspiracies. While most dismissed it as a hoax, others argued that some of his predictions aligned with real-world developments. If time travelers exist, could they be restricted by natural laws, unable to alter key events? Could they be observing history without interference, unable to break the self-correcting mechanisms of time? While there is no concrete evidence proving the existence of time travelers, the grandfather paradox remains one of the biggest hurdles to real-world time travel. If we ever discover a way to manipulate time, we will have to answer a critical question. Does the universe allow us to change the past, or are we forever bound to a predetermined timeline? Whatever the answer, one thing is certain. The debate over time travel is far from over. Now, let's move to another theory that suggests time travel is not only possible but is already happening. Einstein's theory of relativity and the science of time dilation. Einstein's theory of relativity, the science of time dilation. Few scientific breakthroughs have reshaped our understanding of time as dramatically as Albert Einstein's theory of relativity. Before Einstein, time was considered absolute, a constant force that moved at the same rate for everyone, everywhere. But his discoveries revealed a universe far more complex, where time is not fixed but relative, bending and stretching under the right conditions. Could this mean that time travel is not just a fantasy but an actual scientific possibility? If time can slow down or speed up depending on factors like speed and gravity, could we manipulate it to travel into the future, or even the past? To answer this, we need to explore Einstein's groundbreaking theories and how they prove that time itself is far from rigid. Einstein's special and general relativity explained simply. Einstein's theory comes in two parts: special relativity and general relativity. Each plays a crucial role in how time behaves under extreme conditions. Special relativity, published in 1905, introduced the mind-bending idea that time is not the same for everyone. It depends on how fast you're moving relative to something else. The faster you move, the slower time passes for you compared to someone who is standing still. This leads to one of the strangest predictions of relativity, the twin paradox. Imagine two identical twins. One of them boards a spaceship and travels at nearly the speed of light for several years, while the other remains on Earth. When the astronaut twin returns, they will be significantly younger than their sibling. While only a few years may have passed for the traveler, decades could have passed for their twin on Earth. But how can this be possible? It all comes down to time dilation, a real phenomenon confirmed by experiments. General relativity, developed a decade later in 1915, took things even further. Einstein showed that gravity itself affects time. The stronger the gravitational pull, the slower time moves. This means that time passes at different rates depending on where you are in the universe. A clock placed near a massive black hole, for example, would tick much more slowly than a clock on Earth. These discoveries weren't just theoretical. They have been tested and proven repeatedly through real-world experiments, leading to one of the most astonishing scientific confirmations of all time. How time slows down at high speeds. The twin paradox in action. The twin paradox is one of the most famous thought experiments in physics. It asks a simple but profound question: what happens if one twin experiences time differently than the other? Here's how it works. One twin boards a spaceship and travels close to the speed of light. let's say at 99.9% the speed of light, and spends what feels like 5 years exploring deep space. Meanwhile, the twin who stayed on Earth experiences 50 years during the same time period. When the traveling twin returns, they have barely aged, while their sibling on Earth has grown old. Time, for the space traveler, moved much slower than it did for their twin. This isn't just a theoretical idea, it's something we have actually observed in real life. Experimental proof. Atomic clocks and astronauts experiencing time dilation. One of the most compelling pieces of evidence for time dilation comes from atomic clocks, the most precise timekeepers ever built. These clocks can measure time down to a billionth of a second, allowing scientists to test Einstein's predictions with extreme accuracy. In 1971, scientists conducted the Haffler-Keating experiment, where atomic clocks were placed on airplanes and flown around the world. When they returned, the clocks were compared to identical ones that had remained on the ground. The results were staggering. The moving clocks had experienced slightly less time than the stationary ones, just as Einstein predicted. But time dilation isn't just observed in controlled experiments. It's happening right now, with astronauts aboard the International Space Station, ISS. The ISS orbits the Earth at 28,000 km per hour, 17,500 miles per hour. At this speed, astronauts experience a tiny amount of time dilation, meaning that when they return to Earth after months in space, they are fractions of a second younger than they would have been if they had stayed on Earth. Over an astronaut's career, this difference can accumulate to several milliseconds of time travel into the future. But what if we could scale this up? What if we could travel even faster, say, at 99% the speed of light? Would we experience dramatic jumps into the future? Real-world applications. GPS satellites proving relativity every day. If you've ever used GPS to navigate, you've unknowingly relied on Einstein's theory of time dilation. GPS satellites orbit 20,200 kilometers, 12,550 miles, above Earth, where gravity is weaker and their speed is much faster than objects on the ground. Because of this, time moves at a slightly different rate for these satellites than it does for us on Earth. If scientists didn't account for this time difference, GPS systems would accumulate errors of about 10 kilometers per day, making them completely unreliable. To correct for time dilation, engineers adjust GPS satellite clocks to tick 38 microseconds faster per day than those on Earth. This tiny but crucial adjustment ensures GPS remains accurate. This real-world evidence confirms that time does not move at the same rate for everyone. If we could push these limits further, by traveling at near light speeds, we could theoretically leap forward in time, reaching distant futures while aging only a few years ourselves. Controversial insight. Could we manipulate time dilation for controlled time travel? If time dilation is real, and we can observe it on both high-speed travelers and objects in strong gravitational fields, could we intentionally use it for time travel? Theoretically, the answer is yes. If we could develop near-light-speed spacecraft, astronauts could travel deep into the cosmos, returning to Earth hundreds or even thousands of years in the future, while only experiencing a few decades themselves. This means that time travel into the future isn't science fiction, it's science fact, at least in theory. But what about traveling backward in time? This is where things get tricky. Special relativity allows for time dilation but does not permit travel to the past. However, some physicists have proposed that by manipulating wormholes, we might be able to create a bridge through spacetime that connects two points in time. This leads us to the next theory, one that suggests wormholes could act as shortcuts through time, making both forward and backward time travel possible. Could the universe be filled with hidden pathways that connect different moments in time? Let's explore the next mind-blowing theory: wormholes, theoretical shortcuts through spacetime. Wormholes, theoretical shortcuts through spacetime. Time travel has always been a subject of deep curiosity, but one of the most fascinating theories that could make it possible is the existence of wormholes. These hypothetical cosmic shortcuts through spacetime have been at the center of both scientific research and science fiction for decades. If real, they could serve as tunnels between different points in time and space, allowing for faster-than-light travel and possibly even time travel itself. But are wormholes just a theoretical concept, or could they actually exist somewhere in the universe? What are wormholes and how do they theoretically work? A wormhole is a hypothetical passage through spacetime that connects two distant locations instantly, bypassing the usual travel time required to move from one point to another. Think of the universe as a piece of paper. If you draw 2 points on opposite ends and fold the paper so they touch, you create a shortcut. Instead of traveling across the paper, you can move instantly between the 2 points. This is the basic idea behind wormholes, a way to fold space-time and create direct tunnels between different locations in the universe. In theory, if a wormhole connected not just 2 locations in space but also 2 different points in time, it could act as a time machine, allowing travelers to move between past, present, and future. However, while the concept is exciting, the existence of wormholes is still purely theoretical, based on Einstein's equations rather than direct observation. Einstein-Rosen bridges and the concept of space-time folding. The idea of wormholes originates from Albert Einstein and Nathan Rosen, who in 1935 proposed the concept of what is now known as the Einstein-Rosen bridge. This bridge, they suggested, could connect 2 distant points in spacetime through a tunnel-like structure. Their work was based on Einstein's general theory of relativity, which describes how massive objects curve spacetime. If 2 black holes were connected by a bridge, they theorized, it might be possible to travel between them. However, their equations suggested that these bridges would be highly unstable, collapsing almost instantly after forming. Later, scientists refined this idea and suggested that if a wormhole could be stabilized, it might allow for faster-than-light travel, or even movement across different time periods. Some physicists even speculate that naturally occurring wormholes might exist deep in the cosmos, hidden from view but potentially detectable with advanced technology. The biggest problem: wormholes collapse too quickly. While the math behind wormholes is fascinating, there's a major problem: instability. Most theoretical models suggest that wormholes collapse almost instantly. The gravitational forces involved would cause them to pinch shut before anything, whether light, matter, or a spacecraft, could pass through. This makes traversable wormholes impossible under normal conditions. Another issue is that even if a wormhole were large enough to travel through, it would likely create extreme tidal forces that would tear apart anything attempting to pass through it. If wormholes exist naturally, they might be too small and too unstable to be of any practical use. However, some researchers believe that if we could find the right mechanism to stabilize them, wormholes could become a reality. Potential solutions: exotic matter and negative energy. For a wormhole to remain open long enough for travel, it would need to be stabilized with a form of negative energy or exotic matter. This isn't ordinary matter, like the atoms that make up our world, but a hypothetical substance with unusual properties. Negative energy has been observed in small amounts in quantum experiments, such as the Casimir effect, which occurs when two uncharged, parallel plates placed close together create a small vacuum energy. This shows that negative energy does exist, but harnessing it in large amounts to stabilize a wormhole is an entirely different challenge. Some theories suggest that advanced civilizations, perhaps even extraterrestrials, could have already developed the ability to stabilize wormholes using unknown forms of energy. If this were true, it could explain some of the unexplained anomalies observed in deep space. Case study: Kip Thorne's work on traversable wormholes and interstellar connections. One of the most respected physicists to work on wormhole theory is Kip Thorne, a leading expert in astrophysics. Thorne was responsible for some of the most advanced theoretical research on traversable wormholes, meaning wormholes that could be used for travel. His work was not just confined to academic theory, it also helped shape the science behind the Hollywood blockbuster Interstellar. In the film, astronauts use a wormhole near Saturn to travel across the universe, reaching a distant galaxy in a fraction of the time it would normally take. Thorne's research suggested that if an advanced civilization could generate or control exotic matter, a wormhole could be held open long enough for safe passage. However, the energy requirements would be astronomically high, likely requiring technologies far beyond anything humanity currently possesses. Still, the fact that these ideas are being explored at a serious scientific level shows that wormholes are not just science fiction. They are a real possibility within the laws of physics, even if they remain out of reach for now. Controversial insight: have wormholes already been detected in deep space? While we have no direct evidence of naturally occurring wormholes, some astrophysicists believe there may be indirect clues hidden in the cosmos. One of the most mysterious observations in recent years comes from the study of gravitational lensing, where massive objects bend light from distant galaxies. Some researchers have suggested that certain unexplained distortions in deep space could be signs of wormholes, bending light in a way that doesn't match any known phenomenon. Another intriguing possibility comes from black holes. Some theories propose that instead of leading to a singularity, an infinitely dense point of matter, black holes could actually be wormhole entrances that connect different regions of the universe. Could it be that wormholes are already out there, waiting to be discovered? If so, they might hold the key to unlocking the ultimate form of time travel, allowing us to move not just through space, but through time itself. If we ever do find a way to harness wormholes for travel, they could revolutionize our understanding of the universe. The idea that we might one day use cosmic tunnels to visit distant worlds, or even different eras of time, is both thrilling and mind-boggling. But if wormholes don't work, could quantum mechanics provide an alternative path to time travel? That's what we'll explore next in Quantum Time Travel, the role of particles in time manipulation. Quantum time travel, the role of particles in time manipulation. Time travel has long been associated with spaceships, wormholes, and cosmic forces. But what if the secret to time travel isn't in the vastness of the universe but in the tiny, invisible world of quantum mechanics? Unlike the predictable nature of classical physics, quantum mechanics operates under a completely different set of rules, ones that allow for uncertainty, superposition, and even the possibility of time loops. Some of the strangest discoveries in quantum physics suggest that time may not be as linear as we once thought, raising the possibility that time travel might already be happening at the microscopic level. Could the bizarre behaviors of subatomic particles be the key to understanding time itself? And if so, could we one day harness these properties to manipulate time on a larger scale? The weirdness of quantum mechanics and how particles behave differently in time. In classical physics, the science that governs our everyday world follows strict laws of cause and effect. If you throw a ball, it travels in one direction and obeys predictable forces like gravity and momentum. But in the quantum realm, the rules change. Particles can exist in multiple states at once, influence each other over vast distances, and even seem to defy the flow of time. One of the strangest properties of quantum mechanics is superposition, the idea that a particle can exist in multiple states simultaneously until it is observed. Another phenomenon, quantum entanglement, allows two particles to become instantaneously connected, no matter how far apart they are. But perhaps the strangest and most controversial aspect of quantum mechanics is its potential ability to alter time itself. Experiments in quantum physics suggest that the actions we take in the present can affect events in the past, challenging everything we think we know about causality. The delayed choice quantum eraser experiment. Does time work backwards? One of the most unsettling discoveries in quantum physics comes from the delayed choice quantum eraser experiment, an experiment that suggests decisions made in the present can retroactively change events in the past. To understand this, let's first look at the double-slit experiment, one of the most famous experiments in physics. When scientists fire individual photons through a barrier with two slits, the photons behave like waves, creating an interference pattern on a detector screen. But when scientists try to observe which slit each photon goes through, the photons suddenly behave like particles, and the interference pattern disappears. This suggests that simply observing a photon changes its behavior, a strange and unexplained phenomenon. But the experiment gets even weirder with the delayed choice quantum eraser experiment. In this version, scientists use a special detector that records which slit the photon goes through, but only after the photon has already hit the detector screen. The results were shocking. Even though the photon had already passed through the slits, its behavior changed retroactively when the decision to observe it was made later. In other words, it appears that the future decision of an observer affected the past state of the particle. If this phenomenon holds true, it raises a mind-blowing question. Could our choices today be influencing the past? And if the quantum world allows for such time-defying behaviors, could it be possible on a larger scale? The many worlds interpretation. Does every choice create a parallel timeline? Another controversial idea that emerges from quantum physics is the many worlds interpretation, which suggests that every possible event that could happen actually does happen, but in separate, branching realities. Proposed by physicist Hugh Everett II in 1957, the many worlds interpretation suggests that whenever a quantum decision occurs, the universe splits into multiple versions, one for each possible outcome. This means that if you flip a coin, there is a universe where it lands heads and another where it lands tails. This idea fundamentally changes how we think about time and reality. If every possible version of events exists in separate universes, could time travel simply be a matter of moving between parallel timelines? Some physicists speculate that quantum mechanics could provide a framework for a new type of time travel, one that doesn't involve paradoxes like those found in classical physics. Instead of changing the past in our own timeline, a time traveler might instead jump to an alternate timeline where events played out differently. This theory has strong connections to the multiverse hypothesis, which suggests that there could be infinite versions of reality. If true, time travel may not involve changing the past at all, but rather navigating across parallel universes where different histories have unfolded. Scientific experiments hinting at time loops in quantum mechanics. Some experiments hint that the quantum world may already contain time loops, small-scale time travel events that occur at the subatomic level. One of the most fascinating examples comes from research on closed time-like curves, CTCs, theoretical paths in spacetime that allow objects to travel back to their own past. Some scientists have proposed that quantum particles might naturally follow these loops, making tiny, time jumps that could have profound implications for physics. In 2014, a group of researchers led by Seth Lloyd at MIT proposed a quantum model that simulated time travel without paradoxes. Their research suggested that information might be able to travel through time without violating causality, providing a potential way for time loops to exist without disrupting the flow of history. Additionally, experiments with quantum teleportation, where the state of one particle is transferred to another instantaneously, suggest that information might be able to move through time as well as space. If quantum mechanics allows for tiny time loops, could advanced technology scale this effect up? Could we one day create a quantum time machine that allows controlled movement through time? Controversial insight. Could quantum computing lead to breakthroughs in time manipulation? Quantum computing is already revolutionizing the way we process information, solving complex problems millions of times faster than traditional computers. But some researchers believe that quantum computing could also provide new insights into time travel. Because quantum computers rely on superposition and entanglement, they can perform calculations in ways that defy classical logic. Some experts speculate that if we can fully understand the relationship between quantum information and time, we might unlock the ability to manipulate time at a fundamental level. One of the most intriguing possibilities is the idea of quantum memory storage, where data could be preserved across different points in time. If this is possible, could we one day develop technology that allows messages or even objects to be transmitted through time? A famous thought experiment, the quantum time machine paradox, asks, if quantum computers can calculate information across multiple timelines, could they be used to send information backwards in time? Some physicists believe that if we ever achieve full control over quantum mechanics, we might be able to manipulate time in ways we can't yet imagine. While these ideas remain highly theoretical, they suggest that time travel may already be happening at the smallest scales of reality. If quantum physics holds the secrets to time itself, the key to unlocking time travel may not be in massive machines or cosmic wormholes, but in the strange, unpredictable behavior of the quantum world. As we continue to explore the mysteries of quantum mechanics, we might one day find ourselves on the edge of a scientific breakthrough that changes everything we know about time. Now, let's explore a concept that might hold the final key to unlocking time travel. A recently discovered form of matter that appears to defy time itself, time crystals. Time crystals, a new form of matter that defies time. For decades, physicists believed they had a solid understanding of how matter behaves. Everything in the universe was thought to follow fundamental laws of physics, including the rules governing time. But in 2012, Nobel Prize-winning physicist Frank Wilczek proposed something radical. An entirely new form of matter that defies conventional physics and seems to move through time in an entirely different way. These structures, now known as time crystals, challenge the very foundation of what we know about reality. Could time crystals hold the key to unlocking real-time travel? Are they evidence of a deeper, hidden layer of the universe that we have yet to fully comprehend? Scientists at MIT and Google have taken the first steps toward proving their existence, and the implications are nothing short of revolutionary. What are time crystals? A time crystal is a phase of matter that repeats its structure not just in space but in time. Unlike normal crystals, such as diamonds or quartz, which have repeating atomic structures in space, time crystals exhibit a constantly repeating motion without using energy. This discovery is groundbreaking because, according to classical physics, all movement requires energy. A pendulum swings because it was pushed. A planet orbits a star due to gravity. However, time crystals oscillate between states indefinitely, even when they are in their lowest energy state. They are constantly ticking without external input, seemingly defying the second law of thermodynamics, which states that everything eventually succumbs to entropy and disorder. Time crystals appear to exist in a loop, continuously moving without consuming energy. This has led some scientists to theorize that they could be a key to understanding time itself, or even serve as a gateway to controlled time travel. MIT and Google's discoveries on time crystals defying conventional physics. For years, the idea of time crystals was purely theoretical. In 2016, a team of physicists at MIT, led by Norman Yao, proposed a way to create them in the lab. Soon after, scientists at Harvard University and the University of Maryland successfully engineered the first working time crystal, confirming that they were real. In 2021, researchers from Google's Quantum AI lab made an even bigger breakthrough. Using Google's Sycamore quantum processor, they created a time crystal that remained stable and oscillated without energy loss for an extended period. The results were unprecedented. Google's researchers described time crystals as a new phase of matter, unlike anything ever observed before. Their findings suggest that these structures exist outside normal thermodynamic equilibrium, meaning they might be able to interact with time in a fundamentally different way than anything else in the universe. This discovery has led to serious discussions about whether time crystals could be the missing link in our understanding of time and space. If they can maintain constant movement without energy, could they be used to manipulate time itself? How time crystals could be the key to unlocking real-time travel. One of the biggest obstacles to practical time travel is the amount of energy required. Whether it's achieving near-light speed travel, stabilizing wormholes, or creating closed time-like curves, every theory relies on tremendous amounts of energy. Time crystals don't follow these rules, they continue moving through time without consuming energy. Some scientists believe that if time crystals could be scaled up and harnessed correctly, they might act as a medium for controlled time loops. One of the most promising applications of time crystals is in quantum computing. Because time crystals can exist in multiple states simultaneously, they could vastly enhance the processing power of quantum computers, enabling them to perform calculations far beyond what current computers are capable of. More importantly, some researchers speculate that time crystals might be able to store and manipulate information across time. If time crystals allow quantum computers to interact with time in new ways, could they be used to send information into the past or future? Some physicists believe that time crystals might be able to hold quantum memory, allowing for calculations that extend across different points in time. If this proves to be true, it could mean that quantum time travel is possible at an informational level. Scientific controversy. Are time crystals proof of a deeper reality beyond our understanding? The discovery of time crystals has sparked intense debates within the scientific community. Many physicists argue that time crystals challenge fundamental assumptions about the nature of time and energy, forcing a re-evaluation of what is considered possible. If time crystals exist outside normal thermodynamic laws, does this mean we have only scratched the surface of what time really is? Could time, as we experience it, be just a limited perception of a much deeper, multi-dimensional reality? Some researchers believe that time crystals could be the first evidence that our universe operates on deeper principles that we have yet to fully understand. Others propose that they might be tied to the concept of quantum gravity, a long-sought theory that could unify Einstein's general relativity with quantum mechanics. What makes time crystals even more mysterious is that they appear to exist in a form of perpetual motion, yet do not violate known physics. If this is true, could this be the first step toward understanding a new kind of time manipulation? Theoretical applications for computing and potential for time loops. Beyond time travel theories, time crystals are already being explored for cutting-edge applications in technology. Quantum computing could see massive breakthroughs due to time crystals, as they allow for more efficient and stable data processing. Because time crystals can exist in multiple quantum states, they could revolutionize quantum computing, making machines vastly more powerful than anything we have today. Some physicists suggest that time crystals could one day be used to generate stable time loops, allowing for controlled manipulation of time at the quantum level. If this is possible, it could mean that time loops are not just theoretical constructs but something that could be engineered in a laboratory setting. Revolutionizing cryptography is another possibility, as time crystals may enable entirely new forms of data security. If time crystals can store information across different moments in time, they could introduce new ways to secure data, making it almost impossible to hack. While we are still in the early stages of studying time crystals, their existence forces us to rethink everything we know about time. Could they hold the key to unlocking practical time travel? While it may take decades, or even centuries, to fully harness their potential, time crystals prove that time behaves in ways we never imagined possible. If we ever achieve true control over time, it might not come from spaceships or black holes, but from the strange, almost magical world of quantum physics and time crystals. As we wrap up this journey through the most mind-blowing time travel theories backed by science, one thing is clear: time is far more flexible and mysterious than we ever thought possible. Whether through relativity, quantum mechanics, wormholes, or time crystals, humanity is inching closer to understanding time travel as a reality rather than just science fiction. Will we one day master the art of moving through time? Only time will tell. Are we closer to unlocking time travel? Time travel has long been a subject of fascination, not just in science fiction but also in serious scientific inquiry. What was once considered pure fantasy is now a topic of intense research, with some of the world's greatest physicists exploring whether the laws of physics truly allow for movement through time. While no one has yet built a functioning time machine, the theories explored in this journey suggest that time travel may not be as impossible as once thought. From Einstein's relativity and time dilation to the paradoxes that challenge our understanding of causality, from wormholes as cosmic shortcuts to the bizarre behaviors of quantum mechanics, science offers multiple pathways that hint at the possibility of bending time. Perhaps the most unexpected breakthrough comes from time crystals, a new form of matter that defies conventional physics and suggests time loops could be engineered in the quantum realm. Each of these theories brings us closer to understanding time as a malleable force rather than a fixed, unchangeable dimension. If time can be slowed down, sped up, looped, or even manipulated at the quantum level, then the question is no longer if time travel is possible, but rather how we might one day control it. Where modern physics stands on the possibility of time travel, while mainstream physics remains cautious, the scientific community is no longer dismissing time travel outright. The theory of relativity has already demonstrated that time is flexible, with experiments showing that astronauts experience measurable time dilation. The existence of wormholes remains theoretical, but ongoing astrophysical research suggests that if they do exist, they could provide a shortcut between different points in space-time. Quantum mechanics, with its superposition, entanglement, and apparent time-reversing effects in certain experiments, hints that time may not function in a single forward-moving direction. Despite these breakthroughs, several challenges remain. One of the biggest obstacles is causality, the concern that traveling back in time could create paradoxes that defy logic. Some theories, like the Novikov self-consistency principle, suggest that time paradoxes would naturally resolve themselves, while the many worlds interpretation proposes that each time travel event could create a separate parallel reality, preventing paradoxes altogether. Another major issue is energy requirements. Almost every theoretical method of time travel, whether via wormholes, faster-than-light travel, or closed time-like curves, requires amounts of energy far beyond anything we can currently generate. Exotic matter, negative energy, and quantum effects might provide a solution, but these remain in the early stages of research. Despite these roadblocks, physics has continually evolved in ways that defy past expectations. Just a century ago, the idea of black holes seemed absurd, yet today they are widely accepted as real objects confirmed by observation. Could time travel be the next major breakthrough? Why time travel may already be happening, but we can't perceive it yet. If time travel is real, could it be happening right now without us even realizing it? The idea may sound far-fetched, but several scientific theories suggest that time may not function the way we think it does. Time dilation has already been proven, meaning that astronauts traveling at high speeds experience time at a slower rate than those on Earth. This means that, in a sense, they are already traveling into the future, just by a few milliseconds or seconds. While this effect is currently small, it demonstrates that time is not absolute and can be manipulated under the right conditions. Quantum mechanics also raises unsettling questions about our perception of time. If particles can exist in multiple states at once and be affected by future decisions, what does that say about the true nature of time? Some physicists speculate that our limited perception of time may prevent us from seeing the full picture. Time could be layered, nonlinear, or even cyclical in ways we do not yet understand. There is also the possibility that if time travelers exist, they may be bound by rules that prevent them from interfering with observable history. The Novikov principle suggests that time travelers might be able to interact with the past but would be unable to change key historical events, as the universe would automatically correct itself. If this is the case, time travelers could be among us, but we would have no way of proving it. Some theorists go even further, suggesting that time loops may naturally occur on a microscopic scale. Time crystals demonstrate that motion can persist without energy loss, potentially hinting at hidden time loops occurring at the quantum level. If these loops exist, it is possible that time travel already occurs in nature, but at a scale too small for us to detect. If time travel became real, would we even know? Perhaps the most profound question is not whether time travel is possible, but whether we would even recognize it if it were happening. If time travelers have visited the past, could history have already been altered, without us being aware of it? Would we be able to perceive changes in reality, or would our memories and historical records adjust seamlessly to fit the new timeline? Some argue that if time travel exists, it would have to operate in a way that does not allow disruptive changes to history. If an advanced civilization developed the ability to move through time, they might operate under strict rules to prevent paradoxes and maintain historical stability. This could explain why no definitive proof of time travelers has ever been found. There is also the possibility that our current understanding of time is incomplete. We perceive time as a linear progression, moving from past to future, but what if time is actually a fluid, interconnected dimension that can be traversed in ways we do not yet understand? Some physicists have suggested that time might be more like space, with every moment existing simultaneously. If that is the case, time travel may not involve physically moving from one point to another, but rather shifting perspectives within an already existing timeline. As our technology advances, we may uncover clues that time is far more complex than we ever imagined. Quantum computing, advancements in gravitational physics, and new discoveries in the structure of space-time may one day provide the missing pieces to the puzzle. Until then, the mystery of time travel remains one of the greatest scientific questions of our era. If time travel is possible, will we be the ones to discover it, or have time travelers from the future already left their mark on our world? The answers may be hidden just beyond the limits of our understanding, waiting for the right moment in time to be revealed.